Hello, everyone. Today we are going to proceed with vectors in 3D. And we usually, in statics course, when we say vectors, most of the time we mean forces. Sometimes we mean torques, but for the time being, it's basically forces. So last time we saw that if I give you um, you know, 2 points where the force passes through, you can create a unit vector. Today, I'm going to show you two other cases. One of them is pretty straightforward. The second one is a little bit tricky. It's not tricky, but it's like probably you're not familiar with in high school. So basically, let's draw the coordinate system, the rectangular coordinate system, X, Y, and Z as usual. And then I'm going to show you here. So my X, my Y, my Z, and then I have a force, and this force is going something like that along this line. So it's acting on a line like that. And this is in 3D, by the way. So if this is the XY plane and that's the Z plane, my force is something like that. Okay. So if I project it on the XY plane, it falls here. Okay, and maybe I can tell you that the angle it makes with the horizontal plane, this angle, for example, let's give some numbers. So let's say this is 30 degrees. Um, Usually we give you this angle, but I can give you that one. Both of them are 90 degrees, right? The sum of them. So let's say this is 60 degrees. And the force magnitude, whatever, is 150 Newton. And I want to project it and write it in vector form. So I want you to understand that this triangle is an up triangle, something that would look like that in 3D. Okay. So just something to show you. It's a triangle that looks like that. Maybe if I uh, you can see a triangle, assuming this is a straight line. I tried to cut it, but it didn't work. Uh, okay, so let's just, for the sake of clarity, try to make it like that. So it's a line like that in space. So the force is this line, and I can project it, and it would be the bottom line, which is that. And this is the height. Okay, so this force, I can project it on the XY plane, and at the same time, I can project it up to find the Z component. So basically, this angle right here, we usually call it the polar angle. Okay. Sometimes we give you its complement, which is that angle. Of course, if this is 60, that would be 30. This angle right here, and that would be called the elevation angle. Why elevation? Because I had a line in XY plane and then I elevated that by 30 degrees to become that. So either the polar or the elevation, we can give you one of the two. It doesn't matter. You don't have to memorize. You have to think that really I can project this into a component, a vertical component, and a component in the XY plane. And these two angles are 90 degrees. So if I want to project the vertical angle or the vertical component, I'm sorry, the angle between them is 60 degrees. So F sub Z would be 150 Newton times cosine 60 degrees. Notice that when you project and you know the angle between your line or your force And an axis, you multiply by cosine. If you want the other one, you multiply by sine. Likewise, if I tell you, oh, but this angle is 30 degrees, that's the vertical angle or the elevation angle. So cosine 30 will give me that. Sine 30, which is the same as cosine 60, would give me z. Now, so that's easy. Cosine 60 is 1/2, and 150 times 1/2 is 75 Newton. So I found that very easily. Then let's enlarge it a little bit so you can see it better. Then I'm going to project it onto the xy. So if this is f and this guy, or I should have done it slightly. Okay, so if we call that f sub z, then that guy, the dotted line, would be sub f sub xy, meaning the projection of the force onto the xy plane. Like f sub z is the projection of the force onto the z-axis. Okay? So f sub xy would be 150 sine 60 or cosine 30, which is 75 root 3 Newton. Next step is to find the f of x, f of y. Now it's a 2D problem. I have a force in the xy plane. I want to find the x and the y. If you don't want to measure it, you not measure it, meaning try to figure out, there are two ways usually that students use here. I can say, I see that the x component would be positive, right? And the y component would be negative because this is the positive y. And if I project this, I will get x and y, and the y would be pointing in the opposite direction. So I see it visually. That's one way to do it. Another way to do it is to calculate the angle. So let's do the first one. The first one is to say fx equals fxy cosine 30, right? Because the angle is 30 degrees between them. And Fy, I would write negative. Why negative? Because I see when I project it onto, here is the y-axis. The y-axis is here, right? So when I project this line onto the y, it would be a negative y. So I say negative fxy, and the angle is not between them, it's far from them. So I'm going to say sine 30, which is 1/2. And I can use my calculator to find these values, the x and y and the z. So fxy, which is 75 square root of 3, I'm going to multiply it by cosine 30, which is square root of 3 over 2. So I should get what, 112.5 probably? Yeah, 112.5 Newton. Fy would be negative, and then I'm gonna take, oops. Yeah, I can do this and change that into sine instead of cosine. Oops, no. Okay, it doesn't matter, just 3. And then when I come here, I write sine instead of cosine. So that would be 64.95 Newton. So my force as a vector now is f of x 112.5 I minus 6495 j plus 75k Newton. I told you this is the one method that students would look and see if the x is positive or negative, if the y is positive or negative. But the best way, not the best way, but the analytical way, if you don't want to do it yourself, you calculate theta. Remember theta that we used in 2D? It was the angle between the positive x-axis and the projection. But don't tell me it's 30 degrees. No. How did we calculate it? We start from the x, And we went counterclockwise until we got to the force we want. So this is theta, which is a whole circle 360 without the 30. So it's 330 degrees. This is theta. And theta, by the way, since we call this the polar angle or the elevation angle, which is a less common term, but some people use it, especially in engineering, we refer to that as the azimuthal angle. You don't have to remember that. It comes from azimuth, but it's it's counterclockwise, meaning we are in the fourth quadrant. Remember, the fourth quadrant, the cosine, only the cosine is positive and the sine is negative. But the cosine is x. Yes, it's positive, and the sine is y. So at least now we know that the signs would be correct. Let's try to find fx and fy using this method. I'm going to say it's fxy, which is the 75 root 3, cosine 330 degrees, and this is fxy sine 330 degrees. The good part about using the 30 degrees is that you can see whether the x and y is positive or negative, and you do it yourself, right? But you had to add the sign yourself because you see it's going into the negative one. But if you are going to use the azimuthal angle, it will do the work for you. So let's say 75 square root of 3 cosine 330. Guess what? 112.5 exactly. And if you change that into sine instead of cosine, you get the negative sign. So you don't need to add it yourself. You get negative 64.95. Oh, I'm sorry, Newton. I was going to write J. Okay. So now we found for any, so whether I give you, I say it goes from the origin to point whatever, 5, -4, and 7, or I give you these angles, the elevation or the polar angle and the azimuth angle, you should be able to find the force. Again, notice if I ask you, oh, so what is we know the magnitude of the force is 150. So if I divide this by 150, I get cosine theta x, which should be 330 degrees, but you may get it as 30. You get cosine theta y by dividing this by uh, 150, and you get cosine theta z, which we know it's 60 degrees, so it's 1/2, because 75 over 150 is 1/2, and that's basically cosine theta sub z. The second method, as I said, if I give you theta sub x, theta sub y, theta sub z, so I tell you this force makes an angle, say of 70 degrees with the x, 60 degrees with the y, with the z, and whatever with the y. Notice that I cannot give you any three numbers from my head. What did we learn? Just to remind you again, that cosine square theta sub x plus cosine square theta sub y plus cosine square theta sub z equals 1. And this is a universal law that you thought you learn it as a trig identity. Well, it's a much more generic law. So you can add as many dimensions as you want, calculate the angles. I don't know how you do it, but in advanced physics, probably you can find, the angle between some kind of a vector and multi-dimensional universe. And then you would know, at least you would know for sure that the sum square of the cosine of these angles will always add up to 1, whether it's 2D, 3D, 10D. Okay? I hope this was a short one, but at least it covers the area that we didn't finish. Next time we are going to see is it possible to, we learn how to add and subtract two vectors, right? Or two forces or two velocities or what have you. Now, can we multiply them? And if we do, what would be the meaning? If I multiply two vectors, would I get another vector? Would I get something else? And can we divide them? So we are going to look at that in the next video because that would take us a step closer to the actual analysis of objects and structures in this course. Thanks and have a nice day. Bye. Oops.